For our second section on light, we are going to talk about color. As I said earlier and touched on briefly in the past chapter, color is just a difference in the wavelength of light. So different colors correspond to different wavelengths of light, which are absorbed by the cones and interpreted by our eyes to show different colors or different patterns in order to make more sense out of our world. Except for such light sources as lamps, lasers, and gas discharge tubes, most of the objects around us reflect rather than emit light. They reflect only part of the light that is incident upon them, the part that gives them their color. A rose, for example, doesn't emit light, it reflects light. Light is reflected from objects in a manner similar to the way in which sound is reflected from a tuning fork. When a nearby tuning fork sets it into vibration, one tuning fork can make another vibrate even when the frequencies are not matched, although at significantly reduced amplitudes. The same is true of atoms and molecules. The outer electrons that buzz around the atomic nucleus can be forced into vibration by the oscillating electric fields of electromagnetic waves. Once vibrating, these electrons send out their own electromagnetic waves, just as vibrating acoustical tuning forks send out sound waves. Different materials have different natural frequencies for absorbing and emitting electromagnetic radiation. In one material, electrons oscillate readily at certain frequencies. In another material, they oscillate readily at different frequencies. At the resonant frequencies at which amplitudes of oscillation is large, light is absorbed, but at frequencies below and above the resonant frequencies, light is re-emitted. If the material is transparent, the re-emitted light passes through it. If the material is opaque, the re-emitted light returns to the medium from which it came. This is reflection. Usually, a material absorbs light of some frequencies and reflects the rest. If a material absorbs most of the visible light that is incident upon it but reflects red, for example, then it appears red. The color of a transparent object depends on the color of the light it transmits. A piece of colored glass contains dyes or pigments, fine particles that selectively absorb light of certain frequencies and selectively transmit others. A red piece of glass appears red because it absorbs all the colors that make up white light except red, which it transmits. Similarly, a blue piece of glass appears blue because it absorbs all the light of the other colors that illuminate it and transmits primarily blue light. From an atomic point of view, electrons in the pigment atoms selectively absorb illuminating light of certain frequencies. Light of other frequencies is re-emitted from molecule to molecule in the glass. The energy of the absorbed light increases the kinetic energy of the molecules and the glass is warmed. Ordinary window glass is colorless because it transmits light of all visible frequencies equally well. Sun actually emits blackbody radiation, as we were talking about in previous chapters, and plants are green because that's the peak of radiation from the sun and will be the most reliable source of photosynthetic energy. We can, in turn, mostly clearly see yellow-green, as it is important to be able to see different shades of green to eat safely. Our sensitivity to yellow-green light also explains why we see better at night under the illumination of yellow sodium vapor lamps than under tungsten filament lamps of the same brightness. Various amounts of red, green, and blue, the colors of which are three types of cones are sensitive, produce any color in the spectrum. For this reason, red, green, and blue are called the additive primary colors. When two colors are added together and produce they are called white. They are called complementary colors. Every hue has some complementary color that, when added, results in white. So for green, this is cyan. For blue, this is yellow. And for red, this is magenta. Mixing pigments in paints and dyes is entirely different from mixing lights. Pigments are tiny particles that absorb specific colors. For example, pigments that produce the color red absorb the complementary color cyan. And so something painted red absorbs mostly cyan, from which is why it reflects red. In effect, cyan has been subtracted from white light. Something painted blue absorbs yellow and so reflects all the colors except yellow. Take yellow away from white and you've got blue. Cyan, yellow, and magenta are subtractive primary colors. The variety of colors in the color photographs in any book are the result of cyan, yellow, and blue, and or cyan, yellow, and magenta dots. Light illuminates the book, and light of some frequencies is subtracted from the light reflected. The rules of color subtraction differ from the rules of light addition. For example, if you take the three subtractive primary colors and add them all together, you'll get a muddy brown instead of white. This is because it is subtracting away the colors that are reflected rather than adding the colors that are transmitted. Through this, we are able to color print where we take a cyan image, a magenta image, and a yellow image and put and find the amount of each color that is in a color image that we want to print. We then add these together and add a black toner in order to get all of the dark spots and completely print a color picture from these three subtractive colors. With this knowledge of color, we are able to answer some of the questions that you might have as a toddler or as you grow up, such as why is the sky blue? Of the visible frequencies of sunlight, violet is scattered the most in the atmosphere, followed in order by blue, green, yellow, orange, and red. Red is scattered only a tenth as much as violet. Although violet light is scattered more than blue, our eyes are not very sensitive to violet light. Therefore, the blue scattered light is what predominates our vision, and we see a blue sky. There are no blue pigments in the feathers of a blue jay. Instead, there are tiny alveolar cells on the barbs of its feather that scatter light, mainly high-frequency light. So a blue jay is blue for the same reason the sky is blue, scattering. I should also note that the colors red, orange, yellow, green, blue, indigo, and violet are arranged by their wavelength, where red has a high wavelength but low frequency, which corresponds to a lower energy. And indigo and violet have very high uh, frequencies but lower wavelengths. So why are sunsets red? At noon, sunlight travels through the least amount of atmosphere to reach the Earth's surface. Only a small amount of high-frequency light is scattered from the sunlight, all enough to make the sun look yellowish. As the day progresses and the sun descends lower in the sky, the path through the atmosphere is longer, and the more violet and blue are scattered from the sunlight. The removal in violet and blue leaves the transmitted light redder. The sun becomes progressively redder, going from yellow to orange and finally to a red-orange at sunset. Sunsets and sunrises are unusually colorful following volcanic eruptions because particles larger than atmospheric molecules are then more abundant in the air. This is seen in Edvard Munch's, I believe, The Scream, which is believed to have been painted in the wake of a volcanic eruption, which left the sky red in the daylight, even though usually, as we know, it is blue. Why are clouds white? Water droplets are considerably larger than individual molecules and they behave differently. Rather than the scattering that occurs with tiny particles, water droplets primarily reflect and refract light of all colors about equally. The result is a white cloud. Each droplet absorbs a small fraction of the light that hits it, so if you have enough droplets, a lot of absorption occurs. Very little light gets through a really big cloud, which is why it looks dark. A cloud can also be darkened if it is in the shadow of another cloud. A further increase in the size of the droplets causes them to fall as raindrops, and we have rain. This is why dark clouds are omens of later rainfall. And finally, why is water greenish blue? Although water is transparent to light of nearly all the visible frequencies, it strongly absorbs infrared rays. This is because water molecules resonate to the frequencies of infrared. The energy of the infrared waves is transformed into internal energy in the water, which is why sunlight warms water. Water molecules resonate somewhat in the visible red, which causes red light to be a little more strongly absorbed in water than blue light. Red light is reduced to 1/4 of its initial brightness by 15 meters of water. There's very little red light in the sunlight that penetrates below 30 meters of water. When red is removed from white light, what color remains? The question can be asked in another way. What's the complementary color of red? The complementary color of red is cyan, bluish green. In seawater, everything at these depths has a cyan color. Many crabs and other sea creatures that appear black in deep water are found to be red when they are raised to the surface. At these depths, black and red look the same.